Technology, Roorkee, in 2002, followed by his PhD from the same institute on optimal planning and distribution optimal planning of distributed generation system. Dr. Kathod joined Department of Renewable and Hydro Energy of Indian Institute of Technology, Roorkee in 2008. He then joined Department of Electrical Engineering of IIT Roorkee in 2016. His research interests include optimal planning of distributed generation for the distribution network and planning of hybrid and integrated renewable energy systems. He has published more than 35 papers in various journals of repute. He has also presented more than 75 papers in various national and international conferences. He has supervised more than 50 MTech dissertations and 6 PhD theses on his area of research. He has contributed through chapters in 3 books published by Springer. He has also received about 50 research papers submitted to top-rated national and international journals. Dr. Kathod has completed research projects and consultancy assignments worth 2 crore rupees. He has delivered expert lectures in more than 50 workshops and short-term courses and has organized about 40 short-term training courses. He is a member of International Association of Engineers and Institute of Electrical and Electronics Engineers since 2010. With this, I would request Dr. Kathod to please take over the session. Sir.
Thank you, Dr. Rajat. Thank you.
Thank you, sir.
So I hope my slides are visible and I am audible to all.
Yes, sir. Yes, sir.
Okay. So I welcome you all in second day of faculty development program on energy engineering. And today we will discuss about placement of renewable energy based distributed generation in distribution system. So whatever I am presenting, that is actually part of the research work carried out by me and my students. So these are the broad contents of my presentation. First, we will discuss a small brief overview of distributed generation. Then why this DG placement is important. Then different approaches for DG placement. Then we will discuss placement of renewable energy based DGs and different methods for dealing with uncertainty associated with renewable energy based DG. So DG, we can define DG as a small source of electricity which is connected directly to the distribution network or on the consumer side of meter. And different actually organizations and agencies have actually defined DG. So as per SIGRE, it is basically not centrally planned, not centrally dispatched like conventional generators, and generally it is connected to distribution networks, and the size can vary from 50 to 100 megawatt. And in many countries, we use terms like embedded generation, dispersed generation, or decentralized generation in place of DG. So this is the structure of electrical power system. This is the traditional structure. So here we have large generating stations. They are connected to transmission system after reaching the voltage level. And then here we have distribution system which is mostly radial. So here power flow direction is from generating station distribution networks. And we have consumers connected at distribution networks. So power flow direction is unidirectional. But when we are connecting DGs, like here DGs are connected at distribution network. These are the DGs. So what is happening now? The power flow is now no more unidirectional. It is bidirectional. Sometimes the distribution network can take power from transmission system. During some time, when we have surplus generation from DGs, it can inject power to transmission network. So earlier this traditional distribution system was totally passive, but because of this integration of DG, it has become active. So this has actually created several challenges. Presence of DG in a distribution network makes it active network, and there is also bidirectional power flow. So because of that, we have number of issues like voltage rise, reverse power flow, maloperation of protecting device, deterioration of power quality, and then coordination among different DG technologies. We can have a number of technologies for DG, so coordination among those. So now coming to our main topic, that is placement. So why placement of DG is important? So we have few systems. So like here we have a 5-bus network. These are the bus numbers 1, 2, 3, 4, 5, and these are the branch numbers. And here we have the load connected. And load are expressed on the basis of current value for simplicity. So like suppose here at bus number 5 we have 10 ampere current requirement, so that 10 ampere will come from branch number 4. Here we have 10 ampere, so 10, this 10 and this 10, 20 will come through branch 3. 30 here, so 30 plus this 20 will become 50, so 50 ampere will flow through branch number 2. And finally, considering this load, the current through branch number 1 is 100 ampere. And all these 100 ampere will come from substation through basically from transmission system through distribution substation. Now we consider that all branches are having the same resistance, that is 0.1 ohm. So we can compute the total losses occurring in this system, that is simply I square R losses in individual branch, and then we can take the summation of all individual losses. So it is coming to be 1.3 kilowatt. Now consider another situation where we have connected a 100 ampere DG. The DG size is 100 ampere because total load requirement is 100 ampere. So what will happen? The distribution of currents through different branches will remain same because we have connected DG at bus number 1. So it will not disturb the flow of currents through different branches. So there will be no change in the losses. But what is happening here? Earlier we were taking 100 ampere from substation, but now that 100 ampere will be provided by DG. So what is happening here? The stress on substation transformer is released. Consider one more situation. Now here we have connected 100 ampere DG at bus number 5. So now 10 ampere will go to load at bus number 5 and remaining 90 ampere will flow through branch number 4. Now 10 will go here and remaining 80 will flow here. Now 30 will go here and remaining 50 will flow through branch number 2, and this will supply load connected at branch bus number 2. So now here we have great changes in the current flow through different branches. So now again we can compute the losses occurring because this 100 ampere DG is supplying all the load requirements. So there is again no contribution from substation transformer. So if we compute the total losses, so 50 square plus 80 square plus 90 square multiplied by resistance. So it is coming to be 1.7 kilowatt. So when we don't have any DG in the system, losses were actually 1.3 kilowatt, but now it is increased. Now consider one more situation. Here we have connected 100 ampere DG at bus number 3, and we have computed the flow of current through different branches. Like 10 ampere will come from branch number 4, this 10, so 20 will flow through branch number 3. Here we are having 100 ampere, 30 will be consumed here, 20 will be consumed here, so remaining 50 will flow through branch number 2, and it will meet the load requirement at bus number 2. So again, there is no flow of current through branch number 1 and no contribution from substation. So again, if we compute the losses, so it is coming to be 50 square plus 20 square plus 10 square, that is coming to be 0.3 kilowatt. So earlier losses were without DG, it was 1.3 kilowatt. When we placed 100 ampere DG at bus number 5, it increased to 1.7 kilowatt. Now placing the DG of same capacity as bus number 3 has significantly reduced the losses, 1.3 to only 0.3 kilowatt. So this is the importance of appropriate location of DG. Now size of DG is also important. So again, considering one more case, here we have connected 50 ampere DG at bus number 3. Earlier we connected 100 ampere DG. So here we can compute the current through different branches. So 10 ampere will come from branch number 4, and then considering this 10 ampere load at bus number 4, this 20 will come from branch number 3, and here we have 30 ampere load requirement. So 30 and 20 will be supplied by DG. We have one more load connected at bus number 2, so this will be supplied through substation. So again, we can compute the losses. So 50 square, then here there is no current, so no losses. 20 ampere, so 20 square, and finally 10 square. And if we compute, any query? So again, losses are same, that is again 0.3 kilowatt, which is same as we got by placing 100 ampere DG at bus number 3. So what I want to actually explain you that both size as well as location are important for DG. This is a very actually simple system I have considered for demonstration purpose, but in real situation things are not so easy, because distribution system is having so much great number of buses and loads are actually of different types. So it is the placement of DG is actually a highly combinatorial problem. So now in the literature we have actually identified that different approaches for placement of DG. So reduction of power losses is actually a popular objective for placement of DG. Other than this, we have improvement in voltage profile, enhancement in the system reliability, maximization of DG capacity, or minimization of investment towards DG installation. So these are the different objectives have been targeted by researchers. But in this work, mostly we will deal about this objective, that reduction in power losses. And now we have different approaches for DG placement. So those approaches we can classify in different categories like sensitivity index based approach. We identify some suitable buses and then we perform some iterations to decide the capacity. In case of analytical approach, directly we will get the capacity of DG. In case of classical and artificial intelligence based approaches, we have to develop some optimization problem, and then that optimization problem we have to solve either by some classical optimization technique or EI based techniques. So we will discuss each of these very briefly. So sensitivity is basically the impact of change in the system parameter. It could be anything, losses or voltage profile, on system performance. Like suppose if we inject power at a bus, so what is its impact on the performance of the system? And index based methods are basically quite effective. It can tell us about the optimal location, or it can be used to reduce the search space. Suppose we have, let us say, 70 bus system. So it is not possible to consider all 70 buses for DG placement. It will become too complex. So by using sensitivity indexed, we can reduce the number of buses. We can identify few buses which are very sensitive to active power injection or reactive power injection or some other objective. So this will save our computational time also. So suppose we have an N-bus radial distribution system. So these are the load phasor value of load currents at different buses, and these are the phasor branch currents. So now the total losses occurring in the system can be expressed by this expression, that is sum of I square into Ri value of all individual branches. So this is the square of current magnitude flowing through any branch I. Now this current we can express into components like I we can express as its active component and reactive component. So I square will be square of the sum of square of these two components, active component as well as reactive component, as expressed here. Now consider one more case. Now here we have placed a DG at bus number K. So because of placement of DG at bus number K, what will happen? The branch currents will be now changed. So that we have described or designated as I1 new. So this is the new or modified branch currents. And now this is the DG current. Again, we have expressed it with the help of active component and reactive component. And if we assume that power factor is constant, so this we can replace by active component and power factor. So this is the final expression for DG current at bus number K. And now modified current through any branch I will be the previous current before DG placement minus this term. So this term is basically considering that how many buses will be, how many branches will be modified because of DG placement at bus number K. Suppose we are placing bus DG at bus number K. So all these branches between substation bus to bus number K, they will see a change in the branch current. So here DI variable is considering that fact. DI is 1 if branch I, any general branch I, is between bus number 1, that is substation bus, and bus number K. 1 means the current of this branch will be modified. 0, it means it will not be modified. Means for remaining buses which are coming after bus number K, they will not see any change in the current. So now we can compute the losses in the modified network. So for that purpose, we have to take the I square of new current, new branch current, multiplied by corresponding resistance. And now we can substitute the value of this I new in terms of active component and reactive component, which we got from here. This is the active component and this is the reactive component. So now we have two values of losses. One is before DG placement, this one, and this one after DG placement. So we can compute the loss saving, that is the power losses before DG placement minus power losses after DG placement, and we can normalize it. So this is the final expression. We can substitute different expression and finally we will get this expression. So here power loss saving is related to current of DG, branch current, active component, reactive component, and power factor of DG. So by using this expression, we can compute the loss saving provided we know the active component of DG current. So now how we can use this expression? We can perform load flow of base case system without any DG connection in the network. We can compute the branch currents, bus voltages, active power losses, and then we can select a bus. We can vary DG size, and with the help of given expression, we can compute the active power loss saving. And this process we can repeat for all buses, and then we can identify the maximum power loss saving and then corresponding bus and DG size. So this we have performed applied on a 12.66 kV 69 bus radial distribution network, which is having this much load demand with load power factor equal to 0.82. The losses before DG placement are 225 kilowatt and approximately 102 kVAR. And we have considered two different power factors of DG, one at unity power factor, another DG operation at load power factor, that is 0.82. So this is the single line diagram of 69 bus radial distribution network. So first we validated that our expression of power loss saving. So for this purpose, what we did, we selected at a bus, that is bus number 50, and we varied the DG size in percentage of total load 0 to 100% in a step of 5%, and we computed the active power loss saving. So this dotted curve is the active power loss saving by the developed expression, and The solid lines are showing the active power loss saving by performing load flow. We connected a DG and we perform the load flow. So for plotting this curve, we need 20 load flow. So 20 load flow for one bus, and suppose we have 50 buses, so 50 into 20. So this much load flow is required. But in the developed expression only, we need the results of base case load flow and we can compute the loss saving. And both are actually quite close to each other and trends are also similar. So by this way we validated our expression. After that we used to decide the optimal size of DG operated at load power factor. So this is the optimal size at different buses. So optimal size is also varying with respect to bus numbers. And this is the corresponding active power loss saving. It means suppose we are placing a DG of this size at bus number 36, this bus. Here loss saving is 0. Let us consider one more different value. Like suppose we consider this case, bus number 43. So this much maximum loss saving we can achieve by placing DG of this size. So here we can see that we can achieve maximum loss saving of about 90% by placing a DG at bus number 50 of this size. So placement of DG at bus number 50 is will result maximum power loss saving. Similar exercise we executed by considering DG operation at unity power factor. So here also we are getting different DG sizes and corresponding active power loss saving, which is again different for different buses. So here also we are getting this maximum loss saving at bus number 50. So here we can achieve about 60% loss saving if we place DG of 40% of total load at bus number 50. And this is more closer snapshot of active power loss saving and corresponding DG size at bus number 50. When we are operating DG at unity power factor, so this is the maximum loss saving we can achieve, that is about 59% at of this size, about we can say 38 to 39% of total load. But when we place DG at load power factor, we can achieve loss saving about 90%, roughly 90%, by placing DG of size about 47 or 48% of total load. So here power factor of DG is also important to achieve the benefit in the system. So this is how we can use the sensitivity index based approach for identifying the suitable buses and corresponding size of DG. Now let us move to analytical approach. So in analytical approach, what we can do, we can directly we can derive some closed form solutions, closed form equations, and directly by solving those equations we can obtain the solution in terms of dg size. So for this purpose we have to develop suitable expressions based on losses or voltage drop or any other objective that we are going to aim, and then we can solve those developed expression to obtain closed form solution so as to obtain the size and location of dg. So we will extend the previously developed approach. So here we are, what we are doing here, we are allocating mdg simultaneously in n bus distribution network. In previous case, we connected only one DG, but here we are connecting m DGs simultaneously. So again, because of DG placement, the flow of current through different branches will be modified. So the modified current through any branch I can be expressed by this, that is the modified current through branch I, that is previous current minus the current through different DGs with a factor or variable which is taking into account whether that ith branch will be affected or not. Like 1, if ith branch is between bus number 1, that is substation bus, and bus at which kth DG is placed. So here this is actually two-dimensional matrix, and 0 is indicating that ith branch is not affected, and 1 means ith branch is affected because of DG placement at any because of DG placement. So again we can express this with the help of active and reactive component. So this is the active component of modified branch current, and this is the reactive component. And now again we can compute the modified power losses by taking the square of sum of square of losses in individual branches, that is I square R through different branches, and we can substitute the expression here. So this is the modified losses as a function of branch currents before DG placement and active component of DG current and power factor of DG. So like now we can compute the normalized power loss saving, that is the difference of power losses before DG placement and after DG placement divided by losses before DG placement. So we can substitute this different expression, we can simplify. So this is the final expression of loss saving. It is dependent on DG current, active component of branch current, reactive component of branch current, and power factor of DG. Because here we have considered MDGs simultaneously, so here we have terms of all MDGs. Or in other words, we can say we have M number of variables that we have to determine. So now we want that this power loss saving should be maximum. What should be the value of different DG currents so that we can have maximum power loss saving? So this condition we can write mathematically as this, that partial derivative of this power loss saving with respect to DG current, first current, second DG current, third DG current, because we have m DGs, so we will have m such conditions, and all such partial derivative terms should be 0. So by this way we will get m equations and there are m variables, so we can determine the active component of DG currents. So partial derivative of power loss saving with respect to the DG current by any pth DG can be expressed by this. So this is the partial derivative and this should be equal to 0. This we can write in this way also. This is the variable part here because it is containing this term which is related to DG, and second component is this which is actually based on the base case results, that is the branch currents, active component, reactive component before DG placement. So these are basically linear equations. So we will get such m linear equations. So these equations we can arrange in matrix form, like matrix A, that is of m cross m. So that will contain the coefficients of this part. And this is unknown vector that is containing this term for all m DGs, and equal to B, again a vector of size m cross 1, so that is containing this term. This is a constant part. And from this equation we can solve it for unknown vector, that is IADG, by this way. And these are the different entries of matrix A and B and vector IADG. So these entries are basically taken from this equation. So we can solve it for this unknown vector. So we will be able to compute the active component of DG injected currents for all MDGs simultaneously, and then we can compute the DG capacity in MVA by this expression, that is voltage at that bus, active component of DG current computed from this, and then power factor of that DG. Here power factor is assumed to be known, so only we have one variable. We can also solve the same problem considering power factor as variable. So how to use these expression, this algorithm is developed. So first we have to identify m buses, because generally m is very smaller, is smaller than the number of buses in the system. Like suppose we have 50 bus system, so it is not possible to allocate DG at all 50 buses. It can be hardly 2, 3 or 4. So first of all, we have to identify that which are 5, 6 suitable buses for DG placement. So for this purpose, what we are doing, at a time, we are considering first each bus, and we are computing optimal size of DG at that bus using this expression. This is again taken from the developed expression. If we consider m equal to 1, so we can obtain this expression. And also we can compute the real power loss saving. And this process we have to repeat for all buses. After this, once we have completed this procedure for all buses, so we have to select the bus, we have to identify the bus at which we are getting the maximum loss saving. So that bus we select as candidate bus. We place the corresponding computed size of DG at that bus, and we repeat the same procedure again to identify second bus. And this procedure we repeat till we identify M buses suitable for DG placement. After that, we can use this equation to simultaneously obtain the active component of DG currents. So again, this algorithm is tested on 69 bus radial distribution system. So here first we tried to determine the optimal size of unity power factor DG at different buses. So this is the DG size, and these two are actually power loss saving by developed expression as well as by load flow. So here we can identify that in this region we are able to get maximum power loss saving. First of all, here we can see that there is little bit difference in real power loss saving by proposed method and by load flow. This is because in proposed method we have not considered the variation in voltage because of DG placement. In actual practice, what happens when we place DG, so voltage profiles also improves. But while deriving the proposed expression, we have not considered this fact. Otherwise, the expressions will be a little bit complicated. So to simplify, we have not considered the voltage variation. So that is why we are getting slightly different results as by load flow. But trends are similar. So we can use this developed approach for identifying the suitable buses for DG placement. So here we can see that bus number 50 is suitable again for DG placement of this size. So this process we have to repeat several times. So like here we have summary of results. Like we have original base system with this much losses. So first we executed our algorithm to determine 1 DG, and we identified that by placing DG at bus number 50 of this size will cause this much power loss saving. So bus number 1 is this is bus number 50 is our first identified bus. We connected this DG in the system. Again we executed our algorithm. So second we identified that bus number 17 is next most suitable bus for DG placement with this size. So we connected this DG also in the system. Then we tried for third optimal bus. So we got that 39 is suitable. So now we placed this DG also at bus number 39. Again we tried, but here we observed, I think there was very less active power loss saving. So we did not try to search for any more buses. So now we identified that these 3 buses are suitable buses for DG placement. So what we did, we connected, now we used our algorithm to determine the DG size at these buses simultaneously, and we got this result. We connected these DGs at these buses in the system, and we got this much active power loss. So earlier it was 2 to 5, but now after DG placement, we got this much, that is 70.29. Similar exercise we performed considering the DG operation at load power factor. So here the same procedure we applied, and we identified these 3 buses suitable for DG placement, and then we identified the DG size at these 3 buses simultaneously by using our algorithm, and we got this as the optimal DG size. We connected DG at these buses with this size in the system, and we got losses as 5.66. In base case it was 2 to 5, but after DG placement it reduced to 5.66. In previous case also we connected 3 DGs, but losses were actually 70.29. But when DG is operated at load power factor, we can achieve more power loss saving. Now, how we can solve the same problem using classical and AI based approaches. So in this, first we have to develop a suitable optimization problem which can have either one objective or multiple objectives, and there will be some constraints reflecting operational and planning restrictions. And then the developed formulation we can solve by some classical optimization technique, or by using some AI based technique like GA, TS, EP, PSO, ABC, and many more. So again, we are taking the loss reduction as the main objective. So again, we have a model of branch. This is the power flow. This is the load at bus number Q, and this is the power injected at bus number Q. And this is the power flow to other branches connected at bus number Q. So basically this power is basically equal to losses in the branch plus load plus flow to other branches minus injected power. So now we can suppose current is IPQ. So current we can express with the help of this power flow by this expression. And now we can compute the losses. So losses is simply, for one branch it is I square R, and then we can take the summation over all the branches. So this is the final expression for losses in the system in form of power flow. We can use either current or power. So this is our objective. And now constraint. So first of all, power flow balance constraint. So this is the power balance constraint, that power flow, active power flow and reactive power flow is equal to the flow through other branches, load minus injected power plus losses occurring in the branch. Similar relation we have given for reactive power. And this is the flow of power to other branches. That is sum of all flow for which I is equal to Q. And this is the voltage equation that is relating that how the voltage of these two buses are related. So basically this voltage is related to this voltage minus drop occurring in this branch. So this is the voltage equation, and this is the restriction regarding power factor, that we are assuming that power factor is constant. So always this whatever P and Q we are taking from DG, that should maintain this relation. The voltage at different buses should be within their respective minimum and maximum specified limits. Each line is having certain capacity, so current flow through different branches should be within their respective rated capacity. And this total DG capacity, that is the total, this is the MVA capacity of 1 DG, and then summation over all such DGs. So this is actually representing the total MVA of DG, and this part is representing the load, MVA load at one bus. Summation means of total system. So the total DG capacity should be certain fraction of total load requirement of the system. So here XDG is a variable that we can specify, like it could be 30%, 50%. It means that total DG capacity in the system should be within 30% or 50% of total load requirement of the system. So again, this we tested on 69 bus radial distribution network. So first we identified the few buses because it is not possible to consider all 69 buses. So we perform sensitivity analysis. So here we have different buses, and here we have real power loss sensitivity. Real power loss sensitivity means that suppose we inject a very small amount of power at bus number 45. So this is actually, this much change will occur in the losses of system. So negative value is indicating, because here we can see that almost all sensitivity values are negative. It means the losses of the system will reduce. So here we can see that at these buses we can have maximum loss reduction. If we place DG at these buses in this region, we can have maximum loss reduction, because these buses are most sensitive buses.
बेटे वो फंस गया अपनी बात पे, मुझे तत्क्षण कह रहे हैं, बलीन कह रहे हैं.
Reactive power injection as well as here one is reactive power injection, one is real power injection. So with respect to both, these buses are sensitive buses. So among these 54 is one, so we selected 54, and here we can see that here we varied the DG size at bus number 54 from 0 to 2 MVA, and we computed the real power losses. So here, first we are observing as we are increasing the DG capacity, losses are now decreasing. At this point, we are getting the minimum value of losses. And if we further increase the DG capacity, losses will start increasing. So this point is of our interest. This is the case with unity power factor DG. And now this is the case with load power factor DG. So here also trend is similar. That first, with increase in DG capacity, losses are now decreasing. It is minimum at this point. And if we further increase the loss, DG capacity, losses may increase. So these optimal points are different for different power factor of DG. Like here, in case of unity power factor DG, it is near about 1.4 MVA. But in case of LPF DG, it is about 1.8 MVA. So now we executed our algorithm for different cases like single unity power factor DG. So we identified bus number 54 as suitable bus, and this is the optimal DG size. And here we can get about 50% loss reduction. If we place 1.8 MVA DG at bus number 54 and operated at load power factor, we can achieve about 73% loss saving. If we place multiple DGs operated at load power factor at bus number 54 and 53 with these capacities, we can achieve about 82% loss saving. So it is observed that placement of DG at multiple locations is more beneficial as compared to installation of a single DG in the system. And also here we have voltage profile. So this is the voltage profile at base case system without any DG, and here voltage minimum voltage is about 0.91 per unit. When we place DG, so now there is significant improvement in the voltage profile with both types of DG, unity power factor operation and load power factor operation. Now voltage at all buses is more than 0.97 per unit. In case of DG operation at load power factor, we can most of the buses voltage is close to 1 per unit or more than 0.99 per unit. So load power factor DG operation is more beneficial as compared to unity power factor operation. So far we discussed the placement of dispatchable DGs, the DGs which we can control, but in case of renewable it is more challenging because it is difficult to follow a predefined operating strategy. Suppose we are scheduling a DG for, let us say, for tomorrow for, let us say, 2 megawatt. So in case of conventional DG, we can follow that schedule. But in case of renewable energy based DGs, we cannot follow such schedule because most important thing is the availability of that respective resources. So Since the power output from renewable energy based DGs are intermittent in nature, and they depend on the power output also depends on the availability of respective resources. So there are a lot of uncertainties. So while considering renewable energy based DG, we should consider the uncertainties in the power output. So for considering uncertainties, we have different methods like Monte Carlo simulation. So it is a well-known method to obtain a solution from a mathematical model which involves random variables, and Monte Carlo simulation method is considered as a benchmark method. We have probabilistic approach also. In this, we use some mathematical model to compute the expected values of different variables. And again, in probabilistic approaches, we have two types. One is analytical, another is point estimate method. So we will discuss each one by one. So in Monte Carlo simulation, what we do, depending on the given probability distribution of random variables, we randomly sample the values, and those values are assigned to random variables. And now we simulate the actual process. For example, suppose we have solar photovoltaic in our distribution system and we have to compute the losses. And let us say we are considering the time period of 1 day. And we are assuming that for a given hour, the solar radiation is constant. But still we need 24 values of solar radiation, or at least 12 values in which we have sun sign. So what we can do, we can first choose a suitable probability distribution for solar radiation variation. And then from that probability distribution, we can sample 12 values and we can assign to our model. Our model will compute the corresponding power injection, and then we can compute the losses. So this process we have to repeat several times till a predefined convergence criteria is satisfied. But so this is actually best method and a benchmark method also, but it takes a large number of simulations. So it is very intensive to compute, and it is also time consuming. So this is the computational procedure of Monte Carlo simulation. Suppose we have a random variable z of n independent random variables xi. So for any case simulation, we can compute the value of output random variable by this. Here, basically the assigned values of different random variables during case simulation. Suppose we have performed n such simulations, so we can compute the mean value of this random variable, which is our output, and a standard deviation by these expressions. And we have to keep on performing simulations till the ratio of standard deviation to mean of random output variable z becomes less than a pre-specified tolerance. That is the ratio of these to this. Then only we can say that our Monte Carlo simulation is converged. Another method is point estimate method. So it is basically approximate method to solve a probabilistic model. And like in Monte Carlo, we sample values of different random numbers. So here also we use deterministic procedure to solve a probabilistic model by using only few first statistical moment or probability distribution of random variables, such mean that is the first moment, variance second moment, skewness and kurtosis. So in PM, what we do basically, we replace the probability distribution of a given random number or random variable by a finite number of discrete points, 2 points, 3 points, like that. And those points are basically called as concentrations. And by using these points and function, we obtain the information about output variable. Suppose here we have again a random variable z, and it is a function of n independent random variables xi. So this is our input random variables and this is our output random variable. We know the probability distribution of these input random variables. So what we have to do here, for each random variable, let us say xl, we have to compute this function only k times, considering its kth location. Kth location is given by this, that is xlk and mean value of other input random variables. So total number of computations or evaluation of function in of z is basically k into n. For each variable k times, and there is total number of is variable is n. So we have to perform evaluation of function k into n times, like this. Suppose we have taken any nth random variable, so that output is defined by this L comma K, and function is computed by considering mean values of other random variables and standard location of nth random variable. And here L will vary from 1 to n and K will vary from 1 to capital K. And by these relations, we can determine the standard location at which we have to compute the value of function. That is the mu plus these terms. These are also called as standard locations. So suppose we have capital K equal to 3. So we can compute the standard locations using these three relations. And here lambda is basically, it is lambda L comma J is jth standard central moment of random variable xl, which is given by this relation. Once we have computed the value of function, so we can compute the jth moment of output random variable by this expression. This is the value of function we have already computed, and these are the corresponding weights, and these weights are basically computed by these expressions. Now coming to analytical probabilistic approach. So again, it is a approximate method, and in this case also we replace the probability distribution of random variables by finite number of discrete points. The difference between this analytical method and point estimate method is that in case of point estimate method, the number of discrete points is fixed, but here it can be varied from user to user or from application to application. So after selecting some suitable discrete points, what we have to do, we have to take all possible combinations of different these points. And then using these possible combinations, we have to evaluate the function, and then all those individual values we can combine considering the corresponding probabilities, and we can obtain the expected value of output variable. So what are the steps involved here is that first we have to model the location of DG, then we have to model the renewable resources and load, then we have to model the injected power from DG, then we have to combine all three developed models, and then finally we can go for problem formulation. So first we have to model the location of DG. So location of DG is being modeled by a matrix. That is, this is for, here we are considering two types of renewable DGs. One is based on photovoltaic, another is wind. So this is for photovoltaic array. How we are placing in the system? Suppose we have NP number of different photovoltaic types, or we can say NP number of photovoltaic array by different manufacturer, and we have NC locations at which we have to place these NP photovoltaic arrays. So we can have a matrix of size NP cross NC, and a particular individual element Mn of this matrix is indicating that the number of photovoltaic array of type M placed at location N. Similarly, we can model the location matrix for wind turbine also. Here also the locations are same, but here we are considering NW types of wind turbine generators. So AWMN, the number of mth type of wind turbine generator at nth location. So these two matrices are having the same number of columns, so they can be combined in this form also. So this is our total allocation matrix. So now how to model renewable resources and load. So we know that load and basically solar radiation are strongly correlated. They follow some typical pattern. They are correlated. So what we did here, first we divided the steady period of 1 year in 12 months. And then for each month, we subdivided into 24 segments. For means each segment is for one particular hourly interval of a month. So 12 into 24, we have total 288 segments over a year. And for each segment, we are considering different models for solar radiation, wind, and load. For solar radiation, we used beta distribution. For wind speed, we used Weibull distribution. So this is how we modeled solar radiation. For each segment, first we computed the value of alpha and beta, which are parameters of this beta distribution, and then we discretized it into a number of states. Like this is the discrete form of this probability distribution. This is continuous, and that here we have discretized. So a particular solar radiation label and corresponding probability. And we have such pair which is varying from 1 to ns, that is the number of total states. So this is the value of solar radiation, and how we computed the corresponding probability. That for that purpose we used this, that is the integration of this beta distribution function in the for these different ranges as per the value of n. Like for example, this is the continuous probability distribution, and these are the random sample. We have discrete points we are considering. So for this, what will be the probability value? So for that purpose, what we did, we took the area under the curve in this region. So whatever area is coming, that is assigned probability of this state. For this, what we did, we took area under this portion, and that area is assigned as probability of second state, and so on. For last one, what I did, we take the midpoint and we consider the funnel up to funnel point, that is infinite here. So that area is assigned to this funnel point. This I did to ensure that sum of all probability values is equal to 1. This is how I got discretized solar radiation model. It is following beta distribution, and that I discretized in a 15 states. This is continuous function, so that I discretized. So these are the different solar radiation label, and these are the corresponding probabilities. And this model is applicable for a particular segment, like here it is 11 to 12 hours in January. So for January, we have such model for different for each hourly interval. Similarly, now using this solar photovoltaic characteristic, I computed the power output from solar photovoltaic array. So as we know that solar photovoltaic module, just a minute. A typical characteristic that is called as IV characteristic, and it is provided by manufacturer at some specific condition. At different operating condition, the characteristic values may change. It will remain same in shape, but the values may change. So how to obtain those values? So for obtaining those values, we can use these equations. We can compute cell temperature for a given ambient temperature and solar radiation level. We can compute corresponding short circuit current, corresponding open circuit voltage, and finally power output. And this is how we modeled wind speed. So for modeling wind speed, we took Weibull distribution, and this is the model for a particular hourly segment. We discretized it in a similar way as we did for solar radiation. So this is the particular wind speed state and corresponding probability. Probability we computed using this function as given here. And this is a discrete probability distribution of wind speed for period 0 to 1 hour in January. So we have such 288 models. This is one model. This entire curve is one model. So we have total 288 such models for 1 year. And this is the power wind speed characteristic of a wind turbine. And this curve can be mathematically modeled by this equation. So in this region and in this region there is no output. In this region it is non-linear, and when wind speed is between rated to cutout, it is constant, equal to rated power. So it is the same equation. Now, how to model the load? So generally load data is only already in the discrete form. So what we did here, for each time segment we developed discrete load model to load value, load label, and corresponding probability. And this corresponding probability we obtained by this relation that in a given time frame we counted the number of occurrence of load label LNT, this load label, and we divided the same by total number of load points during this time frame. So first we computed the frequency of occurring a particular load label divided by total number of load points during the same time frame. Then we model the injected power from DG units. So we have developed the location matrix for photovoltaic. Now we computed the active power injection. So that is the number of solar photovoltaic array at particular location multiplied by the corresponding power from solar photovoltaic array. So power output is a function of solar radiation level and location matrix. Location matrix is same, but here it is variable. It will vary from state to state and from time frame to time frame. Similarly, we computed the active power injection from wind turbines. So that is location matrix, wind speed state, and here we have considered load also, because for stability regions that the total capacity of wind is restricted to certain fraction of total load. So to consider this fact, we have considered this variable that will limit the wind, that will be either 0 or 1, that we'll discuss later, and the number of wind turbines and the power output from a single wind turbine. Once we have modeled active and reactive components, we can model reactive also. These are the model of active power from photovoltaic and wind. Now we modeled reactive power also. Since we are assuming constant power factor operation, so active power multiplied by 10 into power factor angle. Similarly, for wind turbine also, the active power by this multiplied by 10 of power factor angle. Now, how to combine the different models? So here we can see that our solar radiation state, wind velocity, and load, these are the independent random variables. So any function of these variables is again a random variable. Let us say we are interested in power losses. So power losses will depend on how we are allocating different DGs in the system. What is solar radiation, what is wind speed, what is load value. Out of these variables, this is fixed. This will not vary with time, but these are actually random variables. Just a minute. हेलो, नमस्ते सर। अभी मैं बाद में बात करूँ सर, एक मैं प्रेजेंटेशन दे रहा हूँ अभी कहीं। ठीक है। So the probability, because these are actually defined by, they are having different probabilities. So any function like power loss will also have some certain probability. So that probability, it means that suppose corresponding to these random variables, we have this much power loss. So the probability of occurring of this much power loss corresponding to these random variables is equal to probability of individual random variables. That is the multiplication of probability of individual random variables. So when we are dealing with random variables, we cannot say anything with 100% confidence. Each output is subjected to certain probability. So output of a function of random variable will have probability which is equal to the multiplication of probabilities of individual random variables. So this is for a particular state of solar radiation, wind speed and load. We can combine for a time frame t, we can compute the expected value. How? We have to take different possible values of solar radiation, wind speed and load. Here we are having that I is varying from 1 to NST. All possible states of solar radiation, all possible states of wind speed, all possible states of load for a given time frame. So we will get this power loss, and this is the corresponding probability. That is the probability of individual random variable. So in this expression, we will compute the expected power loss. How we are computing the expected power loss? The power loss value and multiplied by the corresponding probability. So this is the power loss for a particular time frame. Time frame in the sense one segment, like 0 to 1 hour of January. So we will have, as we are having 288 time frames, so we can combine all those to obtain expected active energy losses. That is the losses, expected value of losses for a particular time frame multiplied by the corresponding duration of time frame. That is basically the number of days in a month. And we have to take the summation of over all time frames. So in brief, what I can say, suppose we have wind speed V, we have load, we have two states for wind speed, we have two states for load. So we can have total 4 states. Correct? For wind, let us say we have V1, corresponding probability as P V1, V2, corresponding probability as P V2. Similarly, we have for load also L1, corresponding probability as P L1, L2, P L2. So two possible values of wind speed, two possible values of load. So total possibilities we are having 4. So we can write those V1 L1, V2 V1 L2, V2 L1, and finally V2 L2. What is probability that this will happen? That is the probability of, that is basically probability of P V1 multiplied by T L1. And any output corresponding to these values, let us say it is Z1, will also have the same probability, this probability. So we can compute the output corresponding to each combination Z2, Z3, Z4. Okay, so we have 4 possible values of Z. With these probabilities, we will have the different probabilities. What is the expected value of Z? That is given by summation I equal to 1 to 4, because we have 4 possible values of Z, Zi, and probability of Zi. These are the basically, these values are basically the probabilities of Zi. So this concept is used here basically. Here we have 3 random variables. So this is how we will compute the losses, active power losses, considering the variation in solar radiation, wind speed, and load. So now we are ready with our for our problem formulation. So we have to, what we have to minimize, that we have to minimize the active power losses or active energy losses occurring over the year. So that is our objective, that we have to minimize the energy losses. And now we have to define certain constraints. So here the number of DG units are actually pre-decided, that this much unit we have to install. Like this is the number of solar photovoltaic array of nth type, and this is the number of wind turbine of nth type. So the total number of DGs we have allocated at different locations. So sum of all that is equal to a predefined number. So for each DG type, we have specified a number. Like suppose 2 DGs of a particular type we have to allocate. So where to allocate, that is computed by solving this optimization. And the next constraint is on dispatch wind power. So this is the active power injection by wind turbine at a particular location by a particular type. So we have taken the summation of all such values over all types at all locations. So this is giving the total active power injection by wind turbines. And here it is the load at a particular bus, sum overall, that is the total load in the system, and the load state. So this total value is actually giving the total load of the system. This is basically base case load, and we are considering the load label. So to consider that, we have this variable. So this is representing the total load in the system at a particular instant. So now total active power injection by wind is restricted to certain fraction of total load of the system. This is due to stability consideration. And now we have a power flow constraint. That active power flow through a particular branch between bus PQ is equal to power flow to other branches, load at bus number Q, injected power at bus number Q, and losses occurring in the branch. This is for reactive power, and this is the voltage relation between bus number P and Q. And now we have voltage magnitude limit, that voltage at different buses should be within their specified limits. The power flow, current flow, or we can say MVA flow, should be within restricted capacity. So this is actually a non-linear problem, which is also a combinatorial problem. We can have different combinations, and in fact it is a non-monotonic solution surface. So there can be several local minima. We don't have means uniformly increasing or decreasing surface. So classical optimization technique is not well suited to solve this problem. So here, that is why we are using EP based, that is evaluationary programming based technique. It is basically a part of AI technique and stochastic method, similar to other evaluationary strategy or GA, but the computation mechanism is different than GA. Here we have mutation operator and selection scheme. So how we are going to solve this problem by EP based algorithm? So first we have to the broad steps are, first we have to initialize a population, a number of solution vectors. Then we have to compute the fitness of population. Then we have to create offspring. There will be a competition between initial population, or we can say parent population, and offspring population, and then selection. This process will be repeated till we get the stopping criteria. So how to generate initial population? So we have actually constraint on the number of DG units. So here what we did, here we used a index-based scheme. For example, suppose we have to place 2 DG units at 4 locations. So these are the 4 locations, and we can distribute 2 DGs in these 4 locations. Like here, 1 DG here, 1 DG here. So always we can see in each combination we have total number of DG equal to 2. So here we have total 10 possible combinations. So we have given a unique index to each combination, that is from 1 to 10. So instead of using these combinations, I'm using these indices to as the population in the solution vector. So this is, by this way I initialize the population, like minimum value of index, a randomly uniform number between 0 to 1, maximum value of index, and minimum value of index. Because indices are actually integer value, so we have to take the round off this value, otherwise we can have non-integer value too. So now this is a particular part of initial population, jth element of initial population. So by this expression it is ensured that it is always between minimum and maximum value. So likewise we did for other types of DGs. Now next step is fitness of population. Fitness is actually related to objective function, but sometimes we use penalty function also. So this is the value of fitness, that is the FC, that is our objective function, that is the loss minimization. This is our objective. Also we have considered these two constraints in form of penalty function. This is for penalty for voltage violation, and this is penalty for line loading constraint violation. Penalty means if those constraints are satisfied, it will not impose any penalty. But if those constraints are violated, then these values will be selected in such a manner so that it will disturb the fitness of that ith individual. Like suppose if we talk about voltage magnitude constraint, so if actual voltage is more than the maximum voltage, so it will assign this much value. If voltage is less than minimum voltage, then it will assign this value. But if voltage is within the limit, it will not impose any penalty, so it is 0. So this is for a particular bus, and we have to compute the value for all buses, so that will be the total penalty for voltage violation. And please remember, if all constraints are satisfied at all buses, so it will have 0 value. If constraints are satisfied, so it will have some non-zero value and it is added. Now please remember that our objective is to minimize this. And now here we are adding some non-zero values. So what will happen? This non-zero values in form of penalty, it will disturb the fitness of ith individual. Even though this value is minimum for any particular ith individual, but we have this ith individual is not satisfying a given constraint, so some value is added, so overall fitness will be more. So now that particular ith individual will not be optimal anymore. Similarly, we can compute the penalty for line loading violation. If my actual power flow is more than the specified limit, it will assign some value, and this we have to compute for all the lines in the network. If constraint is not violated, so again it will assign 0. So if all this line loading constraint is satisfied for all the lines, this value will be 0. So if both voltage magnitude and line loading constraint are satisfied for all the buses and lines, so these values will be 0. So fitness value is same as the value of your objective function. Otherwise, the fitness will be disturbed by adding some constants, these values. Now after that, we have to create offspring. So offspring is created from existing population by using a mutation operator. That is basically initial population plus a normally distributed noise we are adding. And we are rounding so that offspring population is also having integer values. And that standard deviation of this normally distributed noise is computed by this expression, that is the maximum and minimum range of jth variable, and this term, that is the depending on the fitness. So this value will vary from 0 to 1. How? Suppose the fitness of this any ith individual is equal to f min, that is the best fit, so this value will be 0. For worst fit, the fitness will be of ith individual will be equal to f max, so f max minus f min divided by f max minus f min, so it will be 1. So basically this value will vary, this term will vary between 0 to 1. 0 for best fit, 1 for worst fit. It means there will be very small perturbation in the individual having best fitness and more perturbation in the individual having worst fit. And this is a constant e to the power r, that is the iteration count. So now we have parent population and offspring population. Now they will play a series of tournaments. And the opponent is also not prefixed, it is selected randomly. So suppose, and on the basis of this performance of tournament, any ith individual will be assigned a score, SI. That is the number of tournaments it has played, and this is the score of individual tournament, which is computed by this. If it is 1, if fitness of ith individual is less than jth or opponent fitness, because we are minimizing our objective function, so minimum value of is desirable. So if fitness of ith individual is less than randomly selected jth opponent, it will have a score 1. Otherwise, it will have 0 score. So all these values are substituted here, and we will have total score of any ith individual. So each individual from initial population as well as offspring population will have such scores. So once tournament is over, all individuals from initial population and offspring population have undergone a series of tournaments. So what we do, we sort different individuals in descending order of their scores, these values in descending order. And then we select high performers, the individuals having high scores equal to the number of population size. Suppose our population size is 10, so initial population will be, there will be 10 individuals. Offspring population will have 10 individuals, so we have total 20 individuals. So based on the score of tournaments, we have to select best 10 individuals for next round, or they will be considered as parents for next generation. So this process we have to repeat several times till the difference between minimum and maximum values of parent population is within some pre-specified tolerance. Their difference is very minimum, means all individuals are having the same, almost same value of fitness function, then only we can terminate this algorithm. Otherwise, we have to perform more and more iterations. We have to generate more offsprings. So now again, this we performed on 69 bus distribution network, and here we need the data regarding solar radiation and ambient temperature and wind speed. So for that purpose, the station at Kandla port of Gujarat is selected, and these are the base case results. This is the total energy losses in a year considering the variation in load. This is reactive power, and this is the power from substation over the year. These are basically energy values, not power values. So megawatt hour, megawatt, and so first of all, because it is not possible to consider all 69 buses for placement, so we performed sensitivity analysis, and we identified that these buses are having these are buses are having best sensitivity value. They will have they are more sensitive to active power injection as well as reactive power injection. And if we install DG at these buses, there will be more power loss saving. Like here also we can see that in this range we are having some suitable buses. Then we can have this range also. Something we can have here, but here we have taken hardly 20 buses. And these are the candidate DGs. We are considering photovoltaic as well as wind turbine. So we have taken two cases. In one cases, we have considered single photovoltaic array and single wind turbine, each of 0.25 megawatt. In second case, we have considered two numbers, two photovoltaic array and two wind turbines, each of 0.125. So total installed capacity is going to be same, that is 0.5 megawatt. And these are the specifications of solar photovoltaic modules. The specification of wind turbine, and the value of wind power to load dispatch ratio is varied from 0 to 40%. That is the restriction on injection of wind power. And the operating power factor of wind turbines is considered as 0.8, while photovoltaic arrays are operated at unity power factor. And the values of different penalty terms for voltage magnitude violation and line loading violation are taken as 100. Here this is selected after a series of trials. Like here, as I told you that this constant selection is very important. They are selected in such a manner so that they can impact this value. In the sense, suppose this value is of order 1000, and this value is coming to be, let us say, point in points. So when this value is added to this, it is not going to make any great impact on fitness of ith individual. So we have to select the value of kV and ks such that they can impact the fitness of ith individual. So they could have some value of kV and ks are selected in such a manner so that they are comparable with this value or order of fitness function. Like suppose if we have 100, so total will be 1100. So now there are little bit difference between these two values. A significant difference is there. So that both penalty terms are taken as 100. So this is optimal location when we don't have, when we have wind power to load dispatch ratio is 0. It means there should not be any power injection from wind turbines. So in that case, there is no wind turbines connected in the system. So we are having these are the location of or optimal buses for placement of photovoltaic array, and these are the buses for placement of wind turbine generators. When we are considering two PVAs and two WTGs, so these are the optimal buses for photovoltaic array, and these are the for wind turbine generators. And these are the convergence. Here we tried for a number of methods, like first we tried EP based method, evolutionary programming. So it converged within 50 iterations. And here we considered only top 25 sensitive buses. We also executed our algorithm considering all 68 buses as candidate locations. So this is the convergence. So it took more than 100 iterations. We also verified our results by using GA, genetic algorithm, taking top 25 sensitive buses, and it is taking about 75 iterations to converge. And here we have comparison by different methods. In first case, we considered all buses as candidate buses. So in EP based method, again, we got this as optimal solution, and it converged in 107 generations, and it took about 109 minutes. If we consider top 25 sensitive buses identified by sensitivity analysis, so locations are same, and EP based method is taking 32 minutes, half an hour. GA is taking 137 minutes, more than 2 hours. And we also perform exhaustive search method. Mean considering all possible combinations. And this is the number of generations, or this is the number of possible combinations we actually computed, and it is taking this much time, about 3700 minutes. So here we can see that now EP based method is now computationally very effective. All methods are giving almost same results, so there is no doubt about the quality of results or quality of solutions. Just a minute. Sorry. So now we can summarize the performance of system. If we allocate one photovoltaic array and one wind turbine generator, so when we have this wind power to load dispatch ratio as 0, energy losses are this much, and base case values are, yeah, these are the base case value, that is 71.83. So it is now reduced to 65.69, and there is reduction from energy from substation also. And this is the value of energy generated from photovoltaic. Wind turbine is 0. As we are increasing the wind power to load dispatch ratio, what is happening? Because there is no restriction on photovoltaic array, so it is the energy generated from photovoltaic array is same for all the cases, but the generation from wind turbine is now increasing. Okay, and because of this, now losses are also decreasing, and the same time the energy from substation is also decreasing. In when we are placing two photovoltaic array and two wind turbine generators for different values of wind power to load dispatch ratio, what is happening? the generation from photovoltaic array is constant. And with increase in wind turbine to wind power to load dispatch ratio, the generation from wind turbine is also increasing. Losses are reducing and energy from substation is also increasing. Now if we compare these two cases, like for this particular value 0.4, so here it is 43.79, but here it is 42.59. 5028 4962. So even though the total capacity of photovoltaic and wind turbine generators are same for both the cases, the difference is that here we are allocating two DGs, one photovoltaic, one WTG, but here we are allocating four DGs, two photovoltaic and two WTGs. And here we can see that locations are also different. In this case, we are restricting to two buses, 50 and 53, but here we are covering four buses, 50, 51, 53 and 54. So now performance of system is improved. And here we have voltage profile. So this is base case voltage profile. And as we are increasing the value of wind power to load dispatch ratio, this is now voltage profile is improving, and best voltage profile is observed when we have WPDLRS 0.4. So what is actually final conclusion? That installation of or allocation of small DGs at different locations is more beneficial as compared to installation of a large size DG at few locations. Or in other words, suppose we want to install a DG of, let us say, 1 megawatt. So we have different options. We can allocate 1 megawatt DG at single bus. We can allocate two DGs of each of 50 kilowatt at two different locations. We can allocate four DGs of 250 kilowatt at four different locations. So that third option is more beneficial in improving the performance of the system as compared to first and second. These are the references which I have used to prepare this presentation. And now, thank you all for your patience. So now, so I have actually completed my presentation. So if you have any query, you can ask. And sorry, I have taken a little bit.
Thank you very much. And I request all the participants to kindly share your queries. So I guess there is no queries from the participants. So I again would like to thank you very much for your informative session and
Thank
giving
you.
important time with us. So, thank you all, sir.
Thank you. Thank you. So I will send the copy of this my presentation so that you can distribute to participants. Will it be fine?
Yes, sir. That would be, sir,
Yeah.
very helpful from your side.
Thank you.
Thank you, sir.
Thank you. So may I leave now?
Yes, sir. Yes, sir. Definitely.
Yeah.
Thank you.